today. Trellis is the core network infrastructure. So jumping right in, what is Trellis? Okay, so it's a unique combination of three. The first one is the Underlay fabric, data center fabric, leaf spine fabric that is built using open source software and bare metal hardware principles. That's the first part. The second part, the virtual network overlay that uses that. And that virtual network overlay comprises of the use of OVS and tunnels. And this is where we do all our virtual, where we do service chaining and things that Larry was talking about. That's how these services in the overlay. And finally, we have unified SDN control, overlay and underlay. Most of the times the overlay and underlay independently, but there are some things that we can do where this unified SDN control over both pieces advantages. And I'll talk about that later towards the end of the presentation. So as I mentioned, Trellis is the enabling network of CORD. And you would have seen times today. And as you can see, has access equipment on one side, whether it's enterprise or mobile access, and on the other side, that connects to the wide area network. In between, it's and switches, and on white box hardware, bare metal hardware, OVS inside each server. So controlled with a cluster of ONOS inside. Apps are running and then orchestrated using XOS. This is the entire CORD architecture, and is this part, right? So it's the infrastructure that control the overlay, that control the underlay, and provide routing services to talk to the outside world. So the rest of my talk is basically going to introduce more details about these three pieces. With the underlay fabric, it was built on bare metal hardware, uses open source, call that white box. There are a lot of folks out there that talk about it really isn't that white. Our definition is that it's a combination of bare metal hardware, software that is giving you this box that you can actually do things if you need it to. That's what makes it white box. This layer 2, layer 3 leaf spine fabric, SDN control, and I'll talk about that in this session. So jumping right in, what today? Well, we're using hardware networks. They're also known as they're subsidiary of networks, and the particular model that we are using is the 60 hardware, which is 40G ports, 30 each. But there is nothing really have to use this hardware. You could use 10G hardware. You could use hardware from a different vendor. It's all good. What happens is that the software stack is exactly the same, whether it's a leaf switch or doesn't, irrespective of the port speed of which vendor you're using for your bare metal hardware. I'll tell you more about the software stack. It that comes from the Open Compute project. It also runs ONI, which is the bootloader to boot Open Network Linux on top of this bare metal hardware. And the use is very common, very widely used. It comes from the Trident Plus line, in the future the Tomahawk line. Typically, if you want to use switch from Broadcom or any other switch ASIC vendor, sign an NDA with them and get access to SDK, right? The stuff that to talk to the chip. But what Broadcom has done over is that they have opened up large parts of and given it access to pretty much anyone use that. So one of them is called OpenNSL. But the one that we actually use is called OFDP. OFDPA stands for OpenFlow Data Path. And the reason why we use OFDPA exposes the Broadcom SDK in open terms. So therefore, we can stick an OpenFlow agent. We use Indigo, and speaks OpenFlow 1.3. So ONOS then has direct programming access to a large part of the direct programming access. Right now, what you will is right. I jumped into telling you about OpenFlow 1.3. I'll come back to that. Just very quickly, let me tell you what the fabric does. It's a layer 2, layer 3 fabric, which means that you can see top of rack switches for each rack. Okay, and in a leaf spine architecture, all of these leaf switches are connected to all of the spines. Okay, so what we do is within a rack, we bridge traffic, right? It's layer 2, it's Ethernet bridging within a rack. But when we start going across racks, it goes into an IP MPLS network. Okay, so it's so your packets hit the top of rack switch. That switch bridges traffic within the rack, but acts as a router to go across racks. We use IP because it scales better than Ethernet, in our opinion. It hashes the packets up to any one of the spines, so a different flow would then hash up to a different spine switch. And at that spine switch, the traffic gets sent back down to the destination rack. Okay, we actually also use MPLS segment routing within the fabric. And strictly speaking, it's not necessary to use MPLS segment routing within that fabric in just this architecture that you see over here. But there are advantages of using MPLS when we start going across central offices, from one central office to another, especially in carrier networks where MPLS is so well established. So now I want to talk about what I was mentioning before about how OpenFlow 1.0, this old 6-year-old version, was very popular, but it had serious shortcomings in that it would only allow you to control one forwarding table in the underlying hardware. But we know underlying the modern ASICs from Broadcom or Marvell or Intel, they have many such forwarding tables and many such other capabilities like being able to broadcast flows or multicast flows or hash them across, right? So there are many port group functionalities as well, okay, that OpenFlow 1.0 did not give you, okay? So we use OpenFlow 1.3 because it gives us that ability to control the entire forwarding table in modern ASICs, okay? So that lets us achieve data plane scale. And we use OFDPA because OFDPA supports OpenFlow 1.3 and gives us access to all of these forwarding tables and port groups. If you go to a vendor today and ask them about their OpenFlow 1.3 support, they'll all say, yeah, we support 1.3. But if you look under the hood, they are still doing what OpenFlow 1.0 was doing. They're still giving you access to only one table. And that is the main reason that we use OFDPA, because we don't have such limitations, and therefore we can scale in the data plane. That's about the data plane. Now let me talk about the control plane, okay, and how we have provided HA scale and performance over there. Now, about the control plane, there are many things that have plagued classic SDN, okay, and there's a couple of myths that I'll talk to you about, okay. People think that in classic SDN, oh, every new packet of a new flow needs to go to the controller, right? And therefore, then they worry about how the controller is in the data path, how things may fall down, how things may not break, how the performance may not be very good. But that's a myth, because what it really is that the applications design the mode of operation for that controller. And we have designed the fabric control application in a way such that these data plane packets never have to go to the controller, okay? So that's one thing. The second thing is people think that, oh, the controllers are out of the network, right? So they're kind of like management stations. And so your network should continue to operate even though your controller goes down, just like, you know, it's like a management station sitting in some NOC somewhere. But the reality is controllers are really network elements, okay? They are really part of the network. They're not some management station somewhere in some NOC, right? They're part of the network elements. And if you look at all of networking, or nearly all of networking, redundancy is almost always two-way redundancy, okay? 1 plus 1, 1:1. It's active, active, active backup, and so on. Nearly all of networking, okay? But because we use ONOS, ONOS does much, much more, right? We can get 3-way, 5-way, 7-way redundancy, okay? No other controller that I am aware of does this, okay? And the bonus is that this n-way redundancy is exactly how ONOS scales as well. So let me show you some examples of what I mean. So here's an instance of a leaf-spine fabric, for example, that is controlled by 5 instances of ONOS that are spread around the data center, okay? So each switch at the same time simultaneously connects to multiple instances of the controller, okay? And one of them is determined to be the master for that switch, and the rest are determined to be backups. Similarly, if you now look from the controller instance side, each controller instance actually connects to multiple switches simultaneously, okay? And if you spread around the mastership over these ONOS instances, that's exactly the same way that it scales. So when things go wrong, so let's say a couple of these ONOS instances just died, okay? There is a 3R recovery process, okay? 3 Rs. First R is the switches redistribute the switch mastership. The mastership for the switches is redistributed. It's done by the controllers, but because the switches simultaneously were connecting to multiple controller instances, the mastership fails over to one of the other backups, okay? Second place, the switches continue to retry the connections that went down to these controller instances that they were formerly connected to. And the final R is the reboot. A management watchdog can reboot lost controller instances, right? So it's showing you, and this is true, that no other controller, SDN controller in the classic sense, actually does this, right? ONOS has this great benefit of this n-way redundancy that allows us to allows us to scale in the control plane and have this HA built into it. So I've just shown you how the underlay fabric, I'll take questions later, how the underlay fabric in Trellis benefits from having both OFDPA for the data plane scale and having ONOS's n-way redundancy and scale for the control plane. Okay, so now let me talk about what comes on top of this. That's the virtual network overlay piece. And as I mentioned before, it comes with OVS and VXLAN and with SDN control. And this is where we do service composition, service chaining. So how do we do that? Okay, here's a picture of 3 racks and say 3 servers inside those racks. And each rack has OVS as the network hypervisor running in there and supporting either VMs or containers. And we can do both. And so we can create tenant networks. It's very well known how to do that with VXLAN tunnels. So you can see that there is a tenant network that is green, where the tenant VMs or containers are spread through the cloud. Similarly, for the tenant network red, the VMs and containers are also spread through the cloud. Okay, now you can imagine that if instead of 9 servers, I had 900 servers, right? That you would have to then create tunnels from every OVS to every other OVS, which means that every OVS would then have to support 900 ports or 900 minus 1 port. But that's not how we do things in Trellis. What we do is we support it with a single VXLAN port. Okay? A single VXLAN port is used where dynamically, when traffic is getting sent through that VXLAN port, we tell it what is the destination of what is the tunnel endpoint destination that you want to reach to, okay? So this massively helps in terms of scalability as well, because when you increase the number of ports in OVS, its performance starts going down. And we do this all with one port. The next thing I wanted to tell you is that, of course, the basic tenets of virtual networking is that we must support address space isolation and overlapping address space, and we do that. But the thing that we do beyond what you will find outside anywhere else with virtual networking is that we also have the ability to do service chaining. Okay? And what is important to understand in Trellis, services have their own virtual network. Okay? And this is where some of the things that Larry was talking about the cloud's best principles comes in, right? Every service can be instantiated by multiple VMs or containers. And that service has its own virtual network that is interconnecting it, okay? And so the thing to understand is that like any of your tenant networks, the service networks can also dynamically shrink and grow depending on the amount of load that is necessary for that particular service. So that's one construction. The second construction is that you have the ability via XOS to be able to say that this is the service graph that I want for a particular kind of traffic. Okay, so this particular service graph says that from the tenant green virtual network, or that particular instance in that virtual network, I wish to go to service Y, but I won't tell you which VM to go to in service Y. Any VM or any container in service Y that instantiates service Y is fine. And then when the traffic comes out of service Y, I want to go to service B. And same thing, I don't have to tell you exactly which VM or container to go to. You can go to any one that instantiates service B. Okay, so you can imagine that there is a load balancing service that happens between tenant green, service Y, and service B. And we have that load balancer actually built in, distributed in every OVS in every server for every service. So when packets come out of tenant green and it's headed to service Y, it goes to the service Y's load balancer that is built into every OVS. It doesn't have to hairpin to somewhere else to get load balanced to an instance in service Y. There is another type of traffic that we actually support, which comes about as a direct connection. Okay, it's not always load balanced. If one service actually needs to provide its service, it needs the help of some other service. So you can see that the actual customer traffic is the gray block that is going from green to service Y to service B. But what happens is service Y needs some other service to provide its own service. Okay, so instead of building that service into the VMs of service Y, that other service, which is service P, has its own virtual network and its own instances. And this is where the microservices architecture is coming in. Instead of putting everything into one VM or everything into one container, you are leveraging this architecture so that service P, which is distinct from service Y, has its own virtual network and its own instances, and service Y is using that to provide the service that it needs to provide for the traffic that is going through the traffic chain. Okay, so all of this magic actually happens inside OVS. It's controlled by this VTN application that runs on ONOS. And just like in the hardware case where I showed you OFTPA being the pipeline inside the hardware, this is the pipeline inside the software. And I won't go through the details, but there is obviously an ingress and an egress pipeline for doing all of this service chains and virtual tenant networking. So if you put it all together, what the traffic looks like is kind of like this. Your traffic is starting off in some VM or container on the left side, and it's headed to some VM or container on the right side. In between, it first hits the OVS, which encapsulates the entire customer traffic into a VXLAN tunnel. Then it hits the leaf switch, which is the hardware platform that does its own routing through the network using not the customer traffic, which is below here, but the encapsulated traffic, encapsulated addresses that OVS puts on it, right? So that's the overlay, and that's the underlay fabric routing. Now, I've kind of talked about the overlay and the underlay as separate instances. In most cases, they are, right? The underlay network is not aware of the virtual networks that are being created in the overlay. It's not aware of the service chaining that's happening in the overlay. But there are a few instances where we can seriously benefit from having this common SDN control over both the overlay and the underlay. I'll show you a couple of instances of that. Okay, so a router, right? Traditionally, you know, a router has a data plane for forwarding packets and a control plane with a variety of protocols that are running, and some outside management system, either the CLI or Netcon or whatever to control it, right? And this is how we have built routers for forever, right? But when we are moving to NFV, okay, there are many, many vendors who will come and tell you that we are going to move this to this, right? Everything that you see on the left-hand side just gets reproduced in software on the right-hand side, right? So your software VM, or VNF is still running all the control plane protocols, and it's still running the same data plane, except everything is now in software, okay? And there are many, many varieties of this that you will find in the industry. Okay, so that's a problem, because once you put this into your data center architecture, now all the traffic, let's say it needs to go to the outside world, has to hairpin through this one VM. Now you can get around this by saying that, well, let's not just have one VM. If you want to scale, if you want to have the performance, let's do this in multiple VMs. Okay, that's feasible. But now this embedded control plane that is in all of these VMs now just got multiplied. You had one instance of this embedded control plane before, and now you have n instances. That increases the complexity. So this is a case where it's really begging for an SDN solution. And that SDN solution would be then to take that control plane out, right, and leave the data plane instances over there so that you can scale. Okay, this still has a problem because now you need a load balancer to go through those n data plane instances that you have. That load balancer may be another appliance that is running in your data center that you have to go through. Trellis does none of this. Okay, it does something similar, but something's entirely different. And we can do this in Trellis simply because we have that common SDN control over both the underlay and overlay. So how does Trellis do virtual routing? Okay, so what you can see here in this picture is that we have some upstream routers in the metro network. Let's see, whoops, I shouldn't have done that. I actually don't know what I did. Okay, we're back, thank you. So we have, I still can't get the laser to work, but that's okay. So what we have is upstream routers in any carrier's metro network, and I need to speak these protocols OSPF and BGP in order to learn what's out there, so I can connect what's inside here to what's out there. Okay, so we use an open source routing protocol stack. We use Quagga, but there's nothing preventing us from using any other open or closed source routing stack. But we have only one instance of that running, not n instances inside the data center. So what we do is this vRouter control application first informs the leaf switch that when you see this control plane traffic, redirect it to Quagga. So Quagga forms the peerings with the outside world, and everything that it learns from there, it then gets fed into the fabric control application and the overlay control application, so that we program not just the hardware, but as well as the OVS to understand that any VM or container running anywhere inside the data center can go to the outside world in a completely distributed manner. You don't have to hairpin through anything else. You don't have to go through any software VM to reach the outside world. Everything gets done in hardware, and it's distributed. So net, we can do this. The Trellis vRouter is essentially one big distributed router. You can imagine that a chassis router has backplanes and line cards. Well, the spine switches in the leaf spine fabric are the backplane, and the leaf switches together with the OVS are the line cards, right? So this entire infrastructure is presented as one big router to the outside world. Okay. One more example of how this common control gives us certain benefits for optimizing certain kinds of traffic. You will hear about residential CORD later in the afternoon from my colleague, Ali. But in essence, what residential CORD is doing is going to your home, right? It's going to your home, you're watching TV, and you're flipping channels. And each channel on that TV is IPTV, right? So it's a IP multicast group that is coming from some IP multicast server somewhere in the metro network upstream, okay? So the way we do this is that when a residential subscriber is flipping channels, that flip is snooped by this multicast control application that is running on ONOS. And if that channel doesn't already exist in the network somewhere, that request is made to the upstream using PIM that, hey, we need this channel because X subscribers X, Y, and Z are asking for it. But at the same time, this multicast control application is telling the Fabric control application that, hey, this channel is about to come in from upstream. Go ahead and program the Fabric such that when it does arrive, okay, that multicast stream gets forwarded through the Fabric and replicated inside the Fabric for whichever subscribers that are asking for that particular channel. So net-net, in residential CORD, Trellis has been customized for IPTV multicast video streams to never have to go through any software VNF or a software switch. It gets entirely forwarded and replicated in the hardware Fabric. Okay, so another example of a customization that was done, that was possible simply because we have this SDN control over both the underlay and overlay. So to summarize, Trellis is a combination, a unique combination of the DC underlay Fabric, the virtual network overlay, and unified SDN control. We've told you about the Fabric having it's layer 2, layer 3. It's built with bare metal and open source with an SDN control plane and modern ASIC data plane, which we can access via the OFTP API. The overlay is designed for NFV with the best principles of cloud, all the things that you talk about when you talk about clouds: orchestration, agility, elasticity, microservices. And this overlay control application called VTN implements and maintains this service graph that actually comes from XOS. So you as the cloud network operator or this CORD operator is going to feed, you're going to feed the service graph to XOS, and XOS will feed it to VTN, and then VTN will handle the programming of the virtual network overlay for whatever service chain you want. And in the data plane, we use OVS and VXLAN and soon DPDK to give us all this magic. And finally, the unified SDN control gives us the ability to optimize certain services, right? Like distributed routing, like multicast IPTV streams. And there are many more, I assure you, there are many more to follow. So thank you.
Okay, I guess.
There was a question over there.
Okay, so we have time for a few questions. Where is Larry? Larry want to join and answer any question for the entire, whatever the infrastructure? Okay, any questions? Oh, go ahead.
So you run the underlay overlay on the same.
The question is, do we run the underlay and the overlay on the same controller? And the answer is that we could. We don't right now, just for separation of concerns and being able to develop the two independently. So those controller instances right now talk to each other. But in principle, there is nothing technically preventing us from running it on the same controller cluster, right? It's never one controller. It's always a cluster of controllers, right? That's the advantage of ONOS.
Do you run underlay inside a core cluster or outside a core cluster?
I'm not understanding your question.
You separate controller running your underlay fabric.
Yes.
Do you run this controller inside your fabric or outside your fabric?
Well, so the Fabric controllers are sitting in servers, right, that are connected in that inside.
Is that part of the fabric?
Yeah, it's part of the Fabric, right?
It's
like I was
inside.
trying to say, the controllers are network elements. You can't really treat them as something like management stations sitting somewhere else.
So then how do you deal with the bootstrapping process? Because
It's an out-of-band network.
You'll hear about bootstrapping this afternoon.
Yeah, there is an out-of-band network between the controllers and the underlay hardware because it just simplifies a lot of issues. We can do it in band, but it's so much easier to do it in out-of-band. And there is a management network anyway that is running everywhere in the data center. So we take advantage of that out-of-band management network to run it. It's connecting all the switches and servers anyway.
Okay, finally our audience is waking up. There are more hands going up. So, okay.
Yes.
Thank you for your presentation. I have two questions. One is about this spinal fabric. So how do you think that you can scale actually to a very large network? Because these spines are connected to all of these fabrics.
Right.
Now assume that you have a very broad network.
Right.
And how can you make sure that these servers actually can be connected?
Right.
Because
So
it employs latency and
Yeah.
Yeah. Okay.
So there's two ways to do it, right? I mean, this is not a new architecture.
What, repeat the question.
Yeah, the question, sorry. The question was, how do you expect the leaf spine fabric to scale to very large data centers? And the answer is, this is not a new architecture, right? All of the Web 2.0 guys are already doing this. And there are two ways to do that. Either you consider that, okay, I'm never going to scale my leaf spine fabric to more than, say, 40 switches or 16 racks, right? So when I need to go more than 16 racks, I go through a router, right? I go through a routed network that is separate from the leaf spine. So the leaf spine fabric is considered as a pod, and then there are multiple such pods connected to a core network, right? That's one way. Another way is to increase the number of layers, right? The leaf spine fabric it's a one-hop thing. You go up to the spine, then you come down to the rack. There are people who have added a third layer, and in fact, they've gone cross-layer. So there's a very good blog on Facebook's website that you can read about, where they are talking about this multi-layer leaf spine fabrics. Okay. Any other question? Yeah.
In the beginning, you mentioned sort of like you can span across multiple central offices using Trellis. So is that running through the WAN or the IP network, or how do you go across?
So you will hear more about it in the ON.Lab section later in the afternoon, where they are starting to explore ways to have multiple central offices connected together across the WAN. Okay. So right now, I would say that Trellis doesn't do that. We are just starting to explore. It's definitely in the roadmap that the ON.Lab people are exploring that, and we bring in those explorations into Trellis that will allow this kind of multi-data center operations.
Let me just quickly, add to that as a consequence, you end up having to splice networks together, which is a really critical role that VTN plays in all of this. That I've taken that carrier Ethernet and spliced it in with the Trellis network. You'll hear a little bit more about that in the platform roadmap and then the OpenCORD session later. Sure.
Yes.
So you mentioned in one of the slides that packages don't go through your controller.
Yes.
Can you explain how that?
Well, so the way the data center is, we take advantage of being in a data center, right? It won't work in, let's say, any generic enterprise network, for example. So what happens is, in a data center, it's a tightly controlled environment. Everything that we are putting into the data center, we are addressing it ourselves, right? We put in a server, we give the server address. We put in VMs and containers, we give the VMs and containers address. So we already know where everything is and how to address it. So if there is any traffic going from one place to another, we know exactly how to get there. So there are never any data plane traffic misses. Now, you could, for example, sit on your computer inside one of the instances and try to address something that doesn't exist in the data center. That traffic will just get dropped, right? It doesn't go to the controller. The controller doesn't try to figure out where in the world this is, because I should know where everything is in my data center.
So essentially, deprogramming everything.
Absolutely. Yeah, this is a proactive mode of operation that SDN can enable, right? Okay.
Okay, maybe last question, and then we should stay on time at least now. Go ahead.
Okay, if I had a purely overlay situation where I don't have control for whatever reason of the interest, typically if I've got a whole bunch of things sitting in but I do have some notion of what types of good for me, like I've got guaranteed bandwidth and latency. in any pair of points. This is really software architecture question. The real question is, can I just take the virtual network overlay and SDN controller and still get a fair amount of functionality out of this?
Absolutely, yes. So,
Repeat, yeah.
okay. So the question is, let's say you only have the virtual network overlay and you did not have control over the underlay, right? But you did know some aspects from the underlay, like some guaranteed bandwidth or some guaranteed latency along some path through the underlay. Can the virtual network overlay still take benefit of that? And the answer is yes, right? We again, like you pointed out, it's a software architecture question, and we haven't quite done that yet, simply because we have that SDN control over both, and we can leverage that SDN control to provide these optimized services. But if the situation comes up where there are operators that say that, hey, we are interested in the overlay, we are interested in what you're doing, but the underlay is under someone else's control, and you don't have control over that, can you provide this kind of functionality? The answer is yes, we can.
I think maybe we should stop.
So, yeah, lunch?
So Bill,
Oh, Bill's going to say lunch, okay.
Lunch should be easy. It's right outside the door.
see you back at 1 o'clock, okay?
Hi, Larry.
Hi.
I'm Sasha Namadi from Xilinx. Yeah, you visit. Yeah, yeah.
I always enjoy your talk.
Oh, thank you.
So I just want to, I was all focused because I find so much of knowledge.
Information coming through. Yeah, there is a
And
lot to get across.
And I think you present it in a very good logical. Most people, they have knowledge, but sometimes it's not building to a story. I think you started with 1, 2, 3.
Have you?
Why 1, why 2?
So we now.
I feel like, so I just
Thank you.
wanted to, so we can get the slides.
Yeah, yeah, they'll put it up somewhere, I'm sure.
So, one of these is
I don't
Absolutely. Hi, Robert. Good to see you again. Yeah.
We're still trying to figure out how to. Still trying to use BNG.
Yeah.
So BNG has a.
Yeah, we'd like
Right.
Now we want to have that control plan is take out. Maybe it's inside this data center or could be somewhere else. That's how.
Yeah.
So that's the.
I'm aware of that scenario, but to be honest, I haven't spent enough time thinking about it because just various things. But it's worth thinking about. I've seen the architecture diagram that you guys have shown, where you're still using the BNG. You have to think about it.
Even in general, sometimes you want to have this. Not
Okay, that's
other CDS also moving somewhere else. So that's the more than inside this.
Yeah. I think we should do a whiteboard discussion to discuss the unique different architecture.
Hi, sir.
From Renaissance?
Yes. Okay. So you brought up an important thing, that whole VXLAN full mesh, right?
Yes.
But the still short than OBS 9 we reach on the other side on one.
Oh yeah, sure. You can still reach everyone else, but you just do it through one tunnel port.
But on the OBS it looks like a single port.
It's a single port.
Okay. And the multiplexing demultiplexing of the standards that choose.
Yeah.
Would that be moved to a VTAP on the leaf or?
Yes, there are people who are talking about that, and that capability does exist on the Broadcom chips.
Yes.
So yes, that is a roadmap item to do hardware VTEPs. It's not for the purpose that you are saying, but it's for the purpose of connecting
What day of the week is
like
it?
hardware
Send me the
appliances,
information.
right?
Part of-
Right.
I'm out
Hardware
there.
appliances to the fabric instead of moving it to a VNF. You still want to use the hardware appliances, but our whole service chaining strategy is dependent on having VXLAN tunnels. So if there is no OVS, if it's not in a server, it's an appliance that is directly connected to the fabric.
You need to beat up it somewhere, right?
Exactly. Right. So the leaf will do that.
So the other aspect of this is the SFF. I don't know, you have service chaining, but the service chaining doesn't seem to go through like an IETF SFF, but really direct chain.
Yes, that's right. Because IETF does not do SDN.
We should find a way.
So we
Tom has
use
been bringing a lot
in
of things
IETF model, the packets themselves carry the information of the service chain in the NSH header. We don't need that special header because we have that
I'd like you to
SDN control, so we can control
From which so
That would be fine.
the intermediate. So in that case, the hardware just looks like an L3 or an L2.
simple. Yeah, there's no need for new hardware for us.
Yes. Okay, very good. Thank you.
Thank you.
Some of the things that we talked about there is expanding, connecting data centers and storage.
Oh,
So very interesting.
okay.
We actually have a virtual
Forward and get into this.
Yeah, that sounds great. Actually, I really think we should attend the e-card sessions that happen in the afternoon. Because
So
that's
part of
what we need.
first of all,
Nice to meet you, John. Yeah. Absolutely. Absolutely. Sorry, I don't have my card. Best is to connect over LinkedIn also. That's the best way. Thank you, John. Nice to meet you.
if I get a traditional microservice architecture,
Oh, okay.
I know about you, you know about we start calling each other. That's you have. That's why we separate the control. The data, the control plane from the
That's in the data
from the
plane.
control plane from the not called the data plane, the service plane. Yes. And although using all the protocols, also we and so you absolutely that is a policy. So yeah, so this is where we go beyond microservices. There is a white paperish thing on the website you should take a look at. It's exactly
Because this has been, I had security for, I'm fixed access, and security, and I'm
so
It depends on the kind of
this
VM,
is
right?
a
So
lot
if
of the
if that VM is meant
foundation
for forwarding,
what triggered a
routing
lot of the way
traffic
the
to the outside world, then it's only done in data plane. In fact, we don't even use that because I said that the forwarding of routed traffic to the outside world actually goes to the hardware. It doesn't go through
bombarded with what subnet are you on, what are the firewall rules, you're running what code, okay. So you have to have an architecture that has multiple security domains. You cannot say it's one big happy family. Now, isolation helps, right? Because your VM is isolated from a resource point of view, from a namespace point of view. But having gotten it there in the first place and set up the virtual network, which is now our implementation of what used to be setting up
So
subnets and
if you
firewalls.
remember what we do for
That's
the
how we do it.
residential card every subscriber
There's one called the security architecture.
has a container. That container called VSG.
easily.
This is virtual service gateway. That's where we implement because the traffic when it moves from the residential subscriber is from the outside world goes through the VSG first. So that's data plane traffic going to VSG and then going to the outside world. But inside the VSG, we also implement other services like, for example, things that you would normally do in the house, like parental controls or something, right? Different DNS, firewalling, right? That's all happening inside the VSG. So that VSG per subscriber basis is handled both control plane and data plane. But there are some control plane things that are not handled inside the VSG. Like authentication of the subscriber actually happens outside. Right?
So the answer is undoubtedly there will be configurations
For authentication, yes. On a per subscriber basis, if there are certain services there. So it's a segregation. Some things we do outside, some things we still do authentication because they just belong there.
And so there will be, I'm not sure what that means.
Yeah, we try to do that as much as we can. Sorry,
I'm Don. And I just realized from your systems, you have.
So I think the other way to look at this, that's why we think of this as a pod. You can think of that as a device that just got plopped down into the office, and there's other devices that we need to use. And so one thing that you can do is do the ECI on the manage it through some higher level orchestration. You chain, you service chain the cord pod, and then there's an interface where you said, okay, I'm going to tag my packets in special place so I know what I'm doing. That's one of them. That's actually well, the controllers are the same. That was just that's something that we also see in interface. Some services are out there. Some services are out there. We use some performance so they can if you think about it, we really need
state management. What the state is saying is about troubleshooting versus the infrastructure.
well, we view it as all authoritative state. If I powered off the infrastructure and powered back on, it can recover from it.
So what we do is, one of our use cases, we take traffic in, and the 40 gig switch level. Those switches have the ability to mirror traffic back to some other place where we could.
But it's good.
Especially if it's a hardware. Doing that in software is even more.
No, absolutely. Yeah. The least, all of the least.
So that's what we're really interested in. If we can get that.
Yeah, we're looking at how do we get on board. We actually use your mix. So that we use the cord, we use your cord.
Hi.
Hello.
So I don't know whose bright idea it was to have 300 people standing. Okay, so
Yeah, I know we've got a lot of that in there.
No,
So I guess we can. I had a question for you. You mentioned that you're in the implementation with OBS.
So what is happening with
So as I'm on
the
that
system? Are the projectors just shutting off?
so this one goes,
it
it says automatically showing up.
top of rack, but normally
When
has
it's
to
on
go
use
through
order,
our router
does
too.
that?
So
Yes, sometimes it does.
that before you send the packet out of that signal,
So it just jumps up with the morning.
Yeah. Power shut off warning, but then the screen still playing.
because at the end of the day, a port is just encapsulation.
I should take
Right? Encapsulation is putting in new addresses, right?
So this one stays on, so the recording stays on.
Address for